final speaker today is Nicolae Tusinschi from OneSpin Solutions, where Nicolae is a product specialist in design verification, and he's going to speak today about verification beyond the core. Nicolae, as I said, is a product specialist in design verification at OneSpin. He joined in 2016 as a QA engineer and developed an exhaustive knowledge of OneSpin's formal verification tools before targeting his focus on the company's OneSpin 360 DV solution. Nicolae holds a BS in Industrial Automation from Dunărea des Jos, University of Galatai, which is in Romania. Apologies, Nicolae, if I mispronounced some of that. And he holds a European Masters in Embedded Computing Systems from Technische Universität Kaiserslautern, Germany. I know that one. And the University of Southampton, which I found easier to pronounce because that's in the UK. So over to you. Thank you very much, Nicolae.
Yeah, cool. Thank you. No worries about the. Yeah. So hello, everyone. Hope everyone is doing okay. Yeah. So what I'm going to talk today is about verification beyond the core, and I have put a tiny agenda for the time that is allocated. So mainly what I will be targeting is the main question of accelerating the SOC verification, trying to get my view, to share my view on the complexity and criticality of SOCs nowadays and why I think automation is the key there. Then we'll briefly guide you through the small case study we performed on a small single core SOC called Filipino from PAL platform, actually, which is from University of Zurich and Bologna, and also how did we deploy the solutions that OneSpin is creating on Filipino. And from that, I will be shift to the next challenge, which is an extension to Filipino. It's called the Hero platform, and that's where the formal connectivity, we brought it to the new level. So we tackled the interconnect challenge on such multi-cluster and multi-core platform. And then we summarize a bit. Before I jump into the, okay, I have this blinking on my side. So before I jump into the talk, so a brief introduction on what we are doing at OneSpin. So at OneSpin, we leverage formal technology in order to develop solutions to target critical hardware verification challenges. And we cover these spaces from the early designer to verification engineers, verify functional correctness, up to the safety, and also later in the flow, the trust and security aspect is also targeted by our engineers in our solutions. And the area of application starts from the 5G IoT going to automotive, industrial, and also latest development in the processor side, where the RISC-V is a new instruction set architecture everyone is looking at. Okay, enough about that. About this, so let's dive into. So accelerating the SOC verification, complexity and criticality. So the complexity and criticality of SOC. So this is creating an increased risk and in functionality, safety, and security. And designers of today's electronics, they simply cannot afford to overlook the integrity of their design in any or all aspects, including correctness, safety, trust, and security. And companies have an obligation to meet these functionality requirements, or they are met with swift ramifications. And we've seen many headlines in the past when something went wrong in the field, and the issue that happened to that device doesn't really have to make the headline, and for the specific case it can be devastating for the company and for people that are working for that organization and so on. Yeah, so meeting these requirements becomes tougher and tougher because the complexity and also because of the innovation progresses. However, the SOCs that empower the 5G, the IoT, and the artificial intelligence are at the core of today's innovation. And these have to be increasingly complex, often with a significantly bigger capacity and power and the ability to be more flexible and customized. So, but even if this complexity and criticality is there, it still is it comes down to the systematic verification flow approach that every organization needs to take into account. So when I'm saying systematic verification flow, it's usually everything will start from requirements, specification, then implementation plan, verification plan developed from that, where different technologies are being deployed in the field, like formal verification, simulation, and others. And then the requirements are broken down into features that are targeted with these approaches. And then in the end, all these results are collected and checked against the sign-off criteria. So accelerating the design verification flow, as I pointed out, this is we're going to target the integration aspect, which is in between the verification and the design specification in this graph. And mainly this will be a talk about the clean integration and how do we ensure reliable integration of design IPs and the range of design verification apps, and also the specialized apps that can be deployed in order to achieve a better integration for the SoC. So the automated formal apps, in OneSpin we have a broad range of automated apps that are part of the design verification, and these can be deployed in the SoC. So this will solve complex error-prone verification issues, and due to the formal technology nature, this is going to have an exhaustive aspect when it comes to testing without significant simulation efforts. And all of these ranges, all of these apps can be deployed depending on where it fits better in the SoC. So it depends on the SoC, of course, but in general, it's applied on the interfaces, the register checking if there's a standard specification, or translate the existing specification is being translated to accommodate the standard and so on. So yeah, why did we started the Filipino project? It was meant to serve as a demonstrator, and I'm going to discuss a bit why did we select Filipino, and the main reason why we selected Filipino for this demonstrator project was that it's open source and it implements, I mean, it's nothing, but it has as a core 2 versions of a RISC-V processor. So yeah, the Filipino is part, as I said already, part of the project started by ETH Zurich and University of Bologna. It's a single core SoC platform. It has two flavors of the core, and one is a 4-stage pipeline, the other one is a 2-stage pipeline. It's a relatively smaller one, but also important is that it has a rich set of peripherals that the guys from Zurich and Bologna have put together in this SoC. Like you can see on the diagram, you have like UART, scope C, you have buses there, you have the core, and it's a good candidate to demonstrate and how the SoC verification should perform from the automated formal apps point of view. So yeah, what is the main approach that we recommend in targeting this question? It is actually everyone needs to plan appropriately in order to make progress quickly. And the target here is to identify areas of design risk, then identify the most straightforward verification process. And yeah, so at OneSpin, we are not excluding simulation as a methodology. So we are well aware that simulation formal can coexist, and formal has its sweet spots to be applied on, especially when it comes to the control part. and simulation is more on the high level, where the state explosion problem will be formal, especially, for example, RAMs when doing formal verification are usually black boxed, so these are not interesting targets for formal verification. But yeah, let's identify the targets. So of course, we started with the CPU, which needed to be verified. We identified the potential AMBA interfaces in the design. We had an XI4 and APB, then I2C was there, SPI, they have both flavors, must translate, and then it follows down to the UART, SOC control, event unit, GPO. Of course, we didn't look at all of them, but they were part of the plan. And how did we apply the solutions that I was mentioning before on this web platform? So we started, as usual, with the low-hanging fruit. So we deployed the safety partial checks on the entire SOC, and of course we then run the reachability analysis, which comes in terms of FSM analysis, the dead code analysis, toggle checks, and it follows the same pattern. So basically, what you need to make sure is that you get rid of these low-hanging fruits as soon as possible, such that they don't propagate further in your verification log. Yeah, so you have the article code, then you go and jumps into the structural analysis, where you do some sort of differential linting. So you fix lint issues and then do the differential analysis and see if the linting issue you had was removed and so on. Safety checks, activation checks, and for issues that you identified, you can debug and fix and then rerun the checks. All right, so when it comes to the formal apps, so now we have, let's say, validated the low-hanging fruit. So the issues that were identified in the first step are validated. And we start usually, as I pointed out, we have the protocol compliance verification that has been applied. The XProp has been applied as well. Connectivity has been applied as well. And we have also the specialized apps like floating point verification. So in this case, floating point was a separate module that was part of the risky, so it was an external one. And this is just a note from my side. This is the early days of the core. So now this is risky core is curated by Open Hardware Group. So and we verified this one with the processor integrity verification as well. So overall, what we applied is, of course, we have the full range of auto checks that have been applied. So the safety checks, reachability in terms of FSM, dead code, stick checks, initialization checks, and differential linting. And from the assertion point of view, we did the protocol compliance for ASI4, protocol compliance for APB, protocol compliance for I2C, XProp checks, interconnect, so the connectivity was verified, and floating point verification, processor verification was there as well. What were some issues that we identified? Of course, I'm not going to report all the warnings and all the potential issues. So these are real issues that are validated, and some of them are fixed by so we have some APB interface violation when party designers introduced. So it's important to run the auto checks. And for example, the unique case statement violation was identified early in the process. And also floating point verification performed showed issues in the FPU. So it is important that you apply this isolated verification in order to make to accelerate the SOC verification later on. And when it comes to the processor, there is plenty of issues that were identified in the processor. So you can look at the risky core GitHub page. So we have reported them, and mainly there is a pattern in this the issues that we identified, and the pattern relies more. It leans towards the exception mechanism, PMPs, and also some wrong results that are written back to the register files. So when it comes to the so this was done on the Filipino SoC, relatively small, very good to use to demonstrate the flow and to identify issues and show value when it comes to how formal can be applied. The same methodology was being applied to larger scale SoC together with the customer. So there's not SoC. The Filipino is just a case study that we use to demonstrate, but real work is done outside together with the customer. Then when it comes to the interconnect, so we verified the interconnect of Filipino SoC. We had some issues there, but they were fixed. And it came up to the, okay, but what if this is getting bigger? And then we thought about the Hero, applying the connectivity, the new connectivity to the Hero platform, and I will introduce you what Hero platform it is. So Hero is a heterogeneous research platform. Its base configuration is for the zinc evaluation kit, features following configuration. So it has a pulp cluster, which the guys from Zurich call it Mr. Wolf, and this comprises 8 32-bit risky cores. And the clusters can be instantiated up to 64. So this is when instantiated, this is becoming quite big. We got quite big design. And our target here was to check how can we easily verify the interconnect. The complexity problem that we are targeting, so in large scale SoC involves this large number of hierarchical levels, and number of connections can get very big. Not all of them are directed type, so it's not straightforward to verify them. So some of them are conditional or delayed. And also, when creating such specification is becoming very complicated. So yeah, and to show you some real data here. So for example, this is the hierarchical view of the instantiated version we did. So we have 2 clusters, and you can see that in each cluster you have 8 cores, and each core has its own part. When we applied the Connectivity XL, and the key benefits of this was that the formal connectivity checking flow, that it scales to extra large chips, so it's delivered convergent proof results in complex connectivity problems, exceed capacity limitations, and reduce the energy engineering effort dramatically. When we applied it, you can see that from the main benefit of Connectivity XL is the easy way to specify. And for example, from 3 lines in the Hero, the tool OneSpin Connectivity XL generates 1032 connections that, when are verified, they are quickly verified in 0.2 minutes. So it's quite performant when it comes. So this was also proven in the field. So with a customer, we have proven the solution running on lots of on a 200 million gates SoC, and with 62 million registers. So it was a good AI, a big chip. So yeah, Connectivity XL is proven to support the auto generation of connectivity tables, millions of RTL instances, fast and reliable formal proofs, thousands of connections per hour being verified. Yeah, summing up, so low effort, high speed, it's very beneficial if formal apps are being applied during the SoC verification flow. So I forgot to mention that this is more bottom-up approach, but yeah, so then worth mentioning that the approach has been applied in several SoC designs, and there are numerous bugs confirmed at least by original designers. All right, so on this note, I would like to thank you everyone. And yeah, so we at OneSpin work towards providing certified IC integrity assurance solutions to develop functional, correct, safety, and trusted design. Thank you very much.
Yeah, well, thank you, Nick. Thank you very much for finishing on time as well. Again, one quick question: You've done this work on publicly available projects. Are you able to share some of the types of bugs that you found on these projects through the tools? I know you on one of the slides you had some, but do you have a complete list of the types of bugs you found?
Yeah, so there was an FPU bug that we reported. There was also an APB violation, and then we had a unique case statement violation that results a violation. This is actually fixed because I reported it and was fixed by the designer from Pulp at that time, I think is, and then this was leading to an unexpected instruction to be decoded in the CPU, and of course many other warnings and stuff like that. But okay. Just this is the real meat there, and not forgetting about the CPU itself.
Okay. And then one quick question from online, just concerned about the use of memory and how that might slow the formal verification down. So how do you handle the memory in the design?
So memories are usually black box, so we don't, when it comes to memories, engineers tend to black box them. So, but yeah, it's a separate discussion. There are a couple of methodologies to simplify, to reduce the memories and so on. So there is approaches and ways of doing it if necessary. But for this specific case, memories were out of discussion for the project.
Okay, brilliant. Thank you very much.